Evening. Welcome to the QCIS channel. We're on this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and what I'm going to do tonight is talk about the engineering design process. Now, when we look at engineering, many of us look at all the calculations that go into engineering, and we also look at the drafting that goes into engineering, but we don't look at the actual process. Where in construction, there's a constructability review. When you're dealing with manufacturing or machinery, you're dealing with prototypes. You're also dealing with the tools that go in to producing a product. And one big tool is the market. Does the market demand that we have a new product, and are we improving old products? But a big aspect is the team. When we deal with engineering, engineering is made up of scientists, researchers, technologists, engineers, and technicians. Everyone has something to offer. Then you have your positions like surveyors, draftspeople, and your inspectors. Now, what I'm going to do is actually get into what the actual engineering design process really is. This is the PowerPoint that I came up with. Now, the outline, discovery versus design, the design process. We deal with specifications, alternatives, implementation, testing, modeling, and simulation. The scientific method is an algorithm or discovery. The engineering design process is an algorithm or design. So when we dive into the scientific method, there are 5 steps that you must utilize. The first one, you observe the environment. Number 2, you invent a tentative description or hypothesis that you're going to describe. Then you use the hypothesis to predict. That's your third item. Then number 4, you're going to test the predictions via experiments, and then you're going to modify the hypothesis. And then number 5, you're going to repeat steps 3 and 4 until the hypothesis agrees with the experiments. Now, when you hear the word hypothesis and experiments, what is that associated with? If you're on your P's and Q's, it's associated with statistics. Statistics is a big part of engineering, particularly if you're going into industrial engineering. Now, when we deal with design, we need to know what the definition of a design is. So the International Technology Education Association design of engineering, or I call it the ITEA, the International Technology Association, or the International Technology Education Association. Getting caught up tongue-tied here, but I'll just utilize an acronym. The ITEA, they design, or they actually define design as the systematic and creative application of scientific and mathematical principles to practical ends such as the design, manufacture, the operation of efficient and economical structures, machines, and processes and systems. So when you hear of the ITEA, where do you see that? You're going to see that in engineering education. Again, so I'll get it right this time. The definition of design, and this is defined by the International Technology Education Association. They define design as the systematic and creative application of scientific and mathematical principles to practical ends such as the design, manufacture, and the operation of efficient and economical structures, machines, processes, and systems. Now, if you think about that definition, what branch of engineering would fit that definition? I have two in mind. When we deal with machines, we deal with mechanical engineering. But when we deal with efficiency, processes, and systems, we deal with industrial engineering and then manufacturing engineering. But there's one more. As we go to number 2, I'm going to use this as an acronym because many of us who have engineering or engineering technology degrees, if we've gone to college, we have what we call a programmatic accreditation, not your school's accreditation, but your programs have accreditations as well. Well, the Accreditation Board for Engineering and Technology is known as ABET. Now, when we deal with ABET, the Accreditation Board for Engineering and Technology, students must be prepared for engineering practice through the curriculum, culminating in a major design experience based on the knowledge and skills acquired in earlier coursework and incorporating engineering standards and multiple realistic constraints. Now, when I look at that, what are they really talking about? They're really talking about the last class that you take in the semester. And what you're doing is you're putting specific courses together that are of interest to you. Let's give you an example. If you are in civil engineering and you want to do structural design, we're going to take all of your structural courses that you have taken in your previous years, and you're going to create a project. This is called your senior design project. And for you to get a degree through an ABET accredited curriculum for engineering and engineering technology, you must have at least 2 semesters of senior design. Now, the first one is going to be maybe 1 credit. You're lining up a project. It's a proposal. Then the second one is worth 3 credits. And you have your instructors. They are going to be your mentors. They're going to tell you how to get through the project. I know I did one. And I went through the design process. And also, your projects could be research projects. Also did a research project. But now we really get more into the design process. And this is where everything starts. If you look at the flow chart, you have to identify the problem. Then you develop specifications. Then you generate design alternatives. Then you have to use models and simulations. Then you implement a prototype. And then you test everything out. And then if you look at all of the blue arrows, they lead to one item. documentation. Now, why is documentation important? Because documentation can be a chronological, it's going to be chronological. And when you document something, that's something that you might need in case you run into a deposition. When I'm out there inspecting a job, it's very important that I am detailed when it comes to documentation. Because everything you're going to document, you're going to have to review. And this is all part of the inspection process in the design. And then you have to form a team. If you look at the top decision boxes for this flow chart, you see form team. Form team goes to identify the problem, and then identify the problem goes back to form team. Well, you need a team to identify the problem. Now, the design objective, it's a big picture of what the design should be able to do. And you have, in terms, basically, nothing specific is going to be in terms of requirements or constraints. And then also, there is no indication as to a particular design solution. Specifications, it's a more precise description of the system, should not imply a particular architecture, but it does provide input to the architecture design process. Specifications may be developed in several ways. You talk directly to customers. You talk to marketing representatives. You provide prototypes to users for feedback. And your specifications may include function and non-functional requirements. And they also may include constraints on the design. Typical project specifications, they're absolute. Others may be negotiable. So you have functionality. That includes inputs, outputs, operating modes. Then you have performance. That's speed, resolution, and latency. Then you have cost, ease of use, reliability, durability, security, fault tolerance. And you deal with the physical. The physical has your dimensions and your mass. And that deals with your size, weight, temperature, and radiation. You have your power, which deals with your battery life and your voltage levels, conformance to applicable standards, capability with existing products. Now, functional versus non-functional requirements. Functional requirements, you deal with output as a function of input. Non-functional requirements, it's time required to compute output, size, weight, etc. Size, consumption, reliability, etc. Now, when we deal with design constraints, as I move it up here so you can see everything, make everything look legible. Course. Basically, multiple constraints usually apply. Constraints are often conflicting. Trade-offs are often needed to satisfy the constraints. Now, here's some examples. Constraints could be physical, economic, environmental, social, time to market, political, ethical, health and safety, reliability, sustainability, manufacturability, and of course, adherence to standards. Now, architectural design. Now, some people might be thinking we're talking about architecture. Well, architecture is not just being applied to buildings, it's being applied to computer architecture. So when you're dealing with a computer, building a computer, what major components go to satisfying the specification? Well, you're going to need hardware components like CPUs and peripherals. You're going to need software components, major problems in their operations. And you must take into account the functional and non-functional specifications. Then you deal with the alternatives. So what you're doing right now isn't working. Consider different design approaches that meet the specifications. Most must involve trade-offs. Some specifications also can be modified while others cannot. Then you have to define your performance metrics that must be met. Also, follow the top-down design process. Partition design into well-defined modules. Also design and test modules independently. Integrate the modules into a system and test the system. And then you must select the components, programming languages, etc., develop versus purchase, and you must utilize the intellectual property. Then we get into the model and simulation. So where prototyping is impractical or it can be expensive, you verify design prior to implementation. Again, where you find prototyping as expensive and impractical, you can verify your design prior to implementation. So you do this by avoiding expensive mistakes. You ensure that your design will meet specifications. And also, some design details are easier to verify in simulation than on a prototype. And then you develop the test for manufacturing the product. Also, you implement the prototype. And implementation should follow naturally from previous design and modeling. So you determine the order in which the models should be implemented and you test at each stage. You also plan ahead for tools needed for implementation, compilers, software tools, chips, sockets, connectors, cables, PC boards, through whole versus surface mount, etc., and test equipment. Now, we are dealing with the design process, but we're utilizing the computer as an example, just so you'll know. And we go into the test and verification. So you must develop a test plan early in the design stage. Incorporate the testability features as necessary. Test throughout design and implementation. Test components independently, and then the integrated system functions. Finally, test to verify meeting of specifications as well as the safety. And you also need to ensure the product is user-proof. Test all external conditions events, and perhaps have non-designers test the product as well. Then you go ahead and utilize general troubleshooting. So you're going to define the problem and the symptoms extent. That's your analysis. So then your synthesis is what model could be causing a problem? And then you have to go to your evaluation stage. Is the cause reasonable? Would fixing it fix the problem? And then you would go to your decision and you select the most likely cause of the problem. And that's where you go to your action. You could repair it, or you could basically get another design. Or you could find something that is already in existence to see how that is functioning. And when an existing product that was in previous design, what test did you take that existing product through, and how did you resolve it? Because then you go to your evaluation, and the problem could be solved. If not, again, just like I mentioned, check another cause. The design process, a teaching tool. Within BEST, the design process can be applied to a robot as a whole. Individual components of the robot, the propulsion, the arm, the grabber, base, etc. The project notebook, the group presentation, the 6 weeks of BEST. Again, within BEST, the design process can be applied to, I'm going to say just about anything. It could be a construction project if you're designing a road. What are you going to utilize for that road? Drainage, kind of pavement markings, signs, etc. Then you go to your encouragement. Have your students formally apply the design process to various aspects of BEST. Have your students document each stage of the design process. Encourage design, but recognize the value of trial and error. Remind students of the gulf between a proposed design and an implemented or functioning design. And very, very important, documentation. Well, in your documentation, you need to know the objective. You need to understand the specifications, requirements, goals, and constraints. Have design alternatives, modeling and simulation results, prototypes. What are your successes and failures? And how are your results from testing? Now, guiding principles. Guiding principles. This is one thing that is very important that people should understand. Because when we add something new, what do we try to do? We try to reinvent the wheel. No, don't reinvent the wheel. Read data sheets and application notes. Reduce your problem to something you've solved before. If you can't meet the specifications, negotiate. Don't hide the problem. Always have an answer because you have to start somewhere. Change one variable at a time when you adjust your design. Build a quick, simple circuit for experimentation. Understand it. Keep design simple. Use multifunction integrated devices when possible. Talk aloud to yourself and team members. That helps spot errors. If you find you've made a mistake, figure out why. Solve the right problem. Act rather than react. Think ahead to prevent problems from cropping up. Redefine print at the bottom of data sheets. When in doubt, don't guess. Look it up and be sure, and then manage your time. And here are all of the references. And this is a big reference right here, as basically we dealt with a lot of the computers. Now, you can use the design process for any product. Now, I'm in the infrastructure or civil engineering arena, so I would apply the same process, but utilize different components. But basically, it's very important that you understand how the design process actually works. Yes, as I mentioned to you earlier, on the education side, we deal with the ABET accreditation. This is when we get into your final project. When we deal with your international education, what we're dealing with are the practicalities that go into your design, like your manufacturing, your process, your efficiency. And again, those come from various areas of engineering. Now, again, engineering is a science. And basically, the three sciences that make up engineering are chemistry, biology, and physics. Then you also include mathematics into engineering. This is why you must be able to complete the science level courses, particularly in your 1 and 200 level classes when you're in college on the undergraduate level, because you are going to see all of that mathematics, all of the theory. Now, understand that engineering is also practicality, because there are some things that you can calculate theoretically, but when you go and test it, you might come out with a different result. And some things you're going to have to use your common sense. See, one thing you need to understand about engineering, and this is part that goes into this right here, the fundamentals of engineering examination, right here. I'm going to take that. Well, fundamentals of engineering examination, you need to know how to look up information. That's what that reference book is for. You are not supposed to memorize anything. Now, you can memorize some equations, like if you are doing fluid mechanics, and I'm told to go find the flow rate. Well, I already know Q equals VA. I could be told to find Q in a different form, where Q equals you're utilizing Manning's equation. Q, depending on if you're using SI or English units, Q equals 1.46 divided by N times A times R subscript H to the 2/3 times S to the 1/2. Now, what does that mean? Well, when I deal with a problem where, let's say, I'm designing a channel and it's going to be a rectangular type of channel. Well, what do I need in order for that problem to work? Well, I'm going to need some information, particularly if I'm going to have a type of shape. Well, this is where the hydraulic perimeter comes into the forefront. Now, what is your hydraulic perimeter? It is your area divided by your perimeter. Now, if I'm going to have a rectangular type of channel, I need to know area. Now, what is the area of a rectangle? Width times length. Now, what is your perimeter? Perimeter is when you add everything up. So when I deal with my hydraulic perimeter or your wetted perimeter. Now, what do I mean by wetted perimeter? I mean the area that's wet, because you can have a rectangular shape, but the whole rectangle is not going to be wet. Just the area that's going to be wet. So what I'm going to do is take the base of the rectangle and I'm going to add 2 times both sides. And that's how I'm going to come up with the wetted perimeter. And then I'm going to take my area and then I'm going to divide it by my wetted perimeter. And then I'm going to plug it into the Manning's equation. That's one area on how you design a channel. So there are some equations that you are going to memorize. Another one, a squared plus b squared equals c squared. Okay, what is that? That's Pythagorean's theorem. X minus b plus or minus the square root of b squared minus 2ac all over 2a. What is that? It's your quadratic equation. So when it comes to engineering, there are going to be units like Celsius and Kelvin. Well, if I have Celsius, how am I going to get to Kelvin? Well, so you understand, when I convert from one temperature to another, I'm going to be adding something. So I'm going to add 273 degrees if I have 100 degrees Celsius, and I'm going to come up with 373 degrees Kelvin. Now, there's also a Rankine scale. And what I'm going to do, I'm going to add 460 to my Fahrenheit scale. Like if I have 212 degrees Fahrenheit. Well, if I add 460 to it, what am I going to get? Well, I'm going to get 672 degrees. That's my Kelvin scale. So engineering is all about taking a lot of the tools that you've learned, putting them together, and creating a project. And you have to make sure that project works. And you have to understand the specifications. And the main specifications, where every specification comes from, is the ASTM. So let anybody tell you anything different. Even when you're utilizing specifications for roadway design, they might tell you, well, when I go take a test, I'm going to use the AASHTO T99. Well, the AASHTO T99 is the same as the ASTM 695. You're just using a standard proctor. And then you're going to have the AASHTO T180. Well, that's the same thing as using the ASTM D1557. But they're both applicable to your design. But that's information on the design process. I just gave you some examples. So if you're interested in engineering, there's a process to getting through the 4 years of college as well, just like the engineering design process. Know that engineering is about the research, teamwork, how you apply the principles, how you read the problems, about it analyzing. It's about coming up with a solution to create a prototype and then a product that is going to benefit the market, something cost effective. And it's also understanding the plans and specifications. And that completes this topic on the engineering design process. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some political and social content, check out my main channel, the 411 Talk Zone Radio Show channel, also here on YouTube. Now, here's where you can find me on both channels. On the 401 Talk Zone Radio Show channel, you can find me on YouTube, you can find me on X, formerly Twitter, Truth Social, and Rumble. And for the QCIS channel, you can find me on YouTube, X, formerly Twitter, and LinkedIn. And I apologize for some of the gaps I had earlier. Had a little issue with Zoom, so I took care of the issue to bring you an educational PowerPoint so you understand how the design process works. Once again, thank you for listening, viewing this content from the QCIS channel. We're on this channel. You get a daily dose of science, technology, engineering, and math. Till next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.